Everybody, we're on 3.2 concavity of the second derivative test. So concavity talks about the curvature of the graph. And there's two types. There is concave up, which means graph looks something like that, like a bowl, or you have concave down. Okay, so concave up, concave down. What that looks like in practice on a graph, the red graph here is our function 1/3 x cubed minus x. If you look at it, and we're analyzing the curvature, you can see this part of the graph is curving down. At this point right here, it switches, and now we are curving up. The curve is facing up. The graph is facing up. If we take f prime of x, and we take the first derivative of it, we drop the 3 down, times 3x squared minus 1. You end up with x squared minus 1. If I then take the derivative of that, so the second derivative, drop the 2 down, I get 2x. Right? That is the green graph here. This graph is y is equal to 2x. It's the second derivative. And the connection I want you to see is if you look at this part of the graph, this is concave down. And the green graph is the second derivative here. It's the graph of 2x. The value of the second derivative is negative because we're below the x-axis. So f double prime of x equals a negative number. When you look at this part of the graph, we are concave up, up. And if you look at the second derivative, it is positive. Okay, so we can come to a conclusion here. Testing for concavity. If the second derivative is greater than 0, in other words, it is positive, then your function is concave up. If the second derivative is negative, below 0, then f of x, it's not f prime of x. Sorry. And f of x is concave down. If you get the rare instance, and it does happen, where the second derivative equals 0, then it's neither concave up or down. Okay? And that actually is an important point that we're going to get to in a sec here. But, all right. How do you find where concavity is, like where do you define what points you're taking your concavity? So we're going to talk about points of inflection or possible points of inflection. So possible points of inflection. In grade 12, we call them POIs, points of inflection, when we did polynomial graphing, when the multiplicity of something was, if you had an x plus 2 to the power of 3, we said the graph came up and it would look like that. We didn't talk about concavity. I'm sure I mentioned it, but we didn't really dive into the details. Now we're going to dive into the details, okay? So possible points of inflection, I'm going to shorthand that to PPOI, okay? Possible points of inflection are similar to critical numbers, except because we're talking about points of inflection or the curvature of the graph. It's when the second derivative is equal to 0 or undefined. Okay? If the concavity changes, then it is a point of inflection. Concavity changes, i.e. you go from up to down or vice versa, then it is a point of inflection, a POI. It's no longer possible. Okay. So let's do practice just finding points of inflection and testing them. Okay. So the first example we're going to do is determine the concavity of f of x is equal to x squared plus 1 over x squared minus 4. Okay, what makes these tricky is you have to do the derivative twice. I am not going to do that because we've finished the derivative unit. You are expected to know how to do this, but if you need, I'm going to give you the answers here. If you need practice, please come see me. I can give you practice. The first derivative becomes negative 10x over x squared minus 4, all squared. That's f prime. You should practice this on your own to make sure you can get that. If you then do the derivative of f primed, you will get f double primed is equal to 10 3x squared plus 4 over x squared minus 4 all cubed. Okay, so where are my PPOIs, my possible points of inflection? So we look at this. Look at the numerator. Does anything make the numerator 0? I look at that, I know the answer is going to be no, but we can test it. So it's either f double prime of x equals 0 or f double prime of x is equal to undefined. So if it's equal to 0, you just look at the numerator. Divide off the 10, you get 0. With the 4 over, you get negative 4. Divide off the 3, you get negative 4/3 x squared. So then you would want to square root it. The problem is that's a negative, so you can't do. Therefore, no PPOI. Okay. On the other side, and you could have figured that out in the beginning by looking at it. When you square something, you always get a positive number. Add it, you're always going to get a positive number. It can never be 0. Okay? All right. So where is the second derivative undefined? Well, then you're looking at the denominator. So you're saying x squared minus 4. Where does that equal 0? Well, that's going to be x squared is equal to 4, so x is equal to plus minus 2. Those are your PPOIs. All right, so just like we did before, our mark them, PPOI. All right, mark them on a number line, negative 2 and 2. I'm going to put the second derivative stuff in the bottom here. And you're testing points just like you did before, because you want to see if the second derivative is positive or negative on that interval. These are not critical numbers. Sometimes they are, but they are not, okay? So, we test this interval. Now, you can test any number in that interval. It doesn't matter. So I'm going to test f double prime of negative 3, and then I test something in this interval. The easiest number would be 0, f double prime of 0, and then something in this interval. Let's test 3. Notice I'm putting them into the second derivative, which is this thing. And all I care about is it positive or negative? Okay? If I put f of negative 3 in, I'm going to get a positive number. Please check that so that you know what you're doing. If its second derivative is positive, that means we are concave up. If I put 0 into that, I get a negative number, which means we are concave down on that interval. And if I put 3 in that number, I get positive, which means we're concave up. Again, they don't always alternate like this, so be careful. Up. That's it. So what I would do on a graph or on a table is I would say this is concave up. Okay. This is concave down, and this is concave up. If you want to know what this graph looks like this. We actually have vertical asymptotes. If you look at the original function, vertical asymptotes at plus minus 2. And the graph looks like this. Concave up from negative infinity to negative 2. The graph looks like that. It's concave down on the next interval, so it looks like that. And it's concave up. Now notice, this is concave up, as is this, but this is an increasing function. So where we're going to get to is later on, the first derivative would be positive, which means the function is going up and concave up. Okay? This is a concave up, but it's decreasing, so the second derivative would be negative, which means it's decreasing. This bit in the middle would actually have a critical number of 0 in there, and so it would be split. This is not part of this unit, but, or 3 point, what are we on, 3.4, whatever this is. This is what we're going to do at the end, put it all together. So the first derivative would be positive here, so the function is increasing. You can see it's increasing, but concave down. It'd be negative here, so it's decreasing and concave down. That's what we're going to. If you want practice, just figuring out the concavity, the curvature of the graph, page 192, 5, 7, and 11. It's just similar to what we just did. You don't have to sketch the graph, just figure out what intervals is it concave up and concave down. All right, take a break, and then we'll talk about second derivative test. Okay, everybody, second derivative test. So, second derivative test says if you have a critical number when the first derivative equals 0, not undefined, we're just going to use the ones that equal 0, then if you plug the critical number c into the second derivative and it's positive, the second derivative is positive means we're concave up. Since that is a critical number, we know it has to be a max or a min. If we're concave up at the critical number, we know we have a minimum. Just like this. Second derivative is positive, so it's concave up, and that's at a critical, therefore you get a min. Conversely, if you put the critical number into the second derivative and you get a negative number, then you know it has to be concave down, okay, at the critical number, which means you have a maximum. If it equals 0, the test fails and you have to use first derivative test. So, here's a question. Find the relative extrema of f of x is equal to negative 3x to the fifth plus 5x cubed, i.e. find the maxes and mins. So we take the first derivative and we get negative 15x to the 4 plus 15x squared. I set it equal to 0. So I factor out a negative 15x squared. I'm going to get critical numbers of 0 and plus minus 1. Those are your crits. Okay? I then take the second derivative of this. Okay? I'm going to get negative 60x cubed plus 30x. All right. I don't care about the possible points of inflection. That's not what this test is for. It's to tell me if I have a max or a minimum. So then all you do is you put your critical numbers into the second derivative. So I go f double prime of 0, f double prime of 1, f double prime of negative 1. If I put 0 in, I get 0. It doesn't tell me any info. We'll deal with that in a sec. That is this last one. Okay. If I put f of 1 in, I get a negative number. All right, which means we are concave down, which means we have a max at that point. All right, we're concave down at the critical number, we have a max. If we put negative 1 in, I get a positive number, which means we're concave up, which means I have a min. Okay? Now, just because it fails, you have to go to the first derivative test. First derivative test, if you remember, if that's my critical number, I test either side of it. Okay? So I'm going to test, and remember we have negative 1 and 1. I've already figured out that negative 1 is a min. So this is a min. Figured out that 1 is a max. Okay, like that. I need to know what's happening here. So I have to test a point on either side. So I'm going to use negative 0.5, which is right there. And I'm going to do positive 0.5. If I put negative 0.5 in, you will find that it is positive, which means the function is increasing. It's going up. If I put 0.5 in, you'll see that it is positive as well, which means it is increasing. So what the heck does that mean? It means we have neither a max nor a min. You'll see at this point it doesn't really make any sense to you, but when we start to curve sketch, you'll see what this means on the graph. So the graph of this function, I don't expect you to know it yet, looks like this. Negative 1, positive 1. Graph looks like this. And then polynomial spins off. But you can see there's your minimum, which we got right there. Okay, concave up. Here's your maximum, which is this one right here. And then at 0, it's increasing on both sides. It's still a critical number because it flattens out. All right. This is called a saddle point. So that's just the saddle point. It is actually a point of inflection if you did the second derivative. So the second derivative is this, negative 60x cubed plus 30x. Negative 60x cubed plus 30x. And if I set that equal to 0 and took out a 30x, I'd get 2 negative 2x squared plus 1. So you would get possible points of inflection of x is equal to 0 for this one. All right, that's why this shows up. It's a point that actually turns out to be a point of inflection because the curvature changes. And if you did it on this one, you move the 2x over, you're going to get 1 is equal to 2x squared. So you need 1 over root 2 is equal to x, okay? Which is plus or minus this point right here. And this point right there. Curvature changes. We're getting into the weeds here a bit, but this is what's coming. You can see the curvature of this graph is concave up. At this point, it changes to concave down. So that is the PPOI. Same with this, concave down. There, it's concave up. Right? Practice those questions. This is what's coming down. We're going to start to put all of this together soon. There's 35, 37, 51 to 55 odd, 75 and 77. All right, enjoy, people.